Hey Beachemsters, this is Mrs. Vandelay bringing you Blankwalle 11, Chapter 11, Section 5, Part 3. Hopefully this is the last one. So the Clapeyron equation helps you to actually calculate the heat of vaporization for different liquids. All you need is a pressure temperature probe from Vernier, all right? And you can do that. Of course, you have to manipulate the axes, but we can do that later. So again, it relates the vapor pressure of a liquid and its temperature. So if you look at the above graph, what above graph? Let me show you. This above graph, okay? It's not linear, okay? So we can't really put a y equals mx plus b to this, all right? But there is a relationship between vapor pressure and temperature. And notice that we have diethyl ether, which is dipole, ethyl alcohol, hydrogen bonding. Here's water with H2O. Ethylene glycol actually has two OH groups on it, so it has greater hydrogen bonding. So anyway, the point is there a relationship between these curves here and the heat of vaporization? The answer is most definitely yes. So what is that relationship? Well, that's what the Clapeyron equation will tell us. Let's go back to the next page. All right, so if I manipulate the variables and use some calculus, you can make a linear relationship. So here is the Clapeyron equation. The natural log of P of vaporization is equal to the negative delta H vaporization over R times 1 over T plus ln of beta. Do you think we really care about beta? And the answer is no, it has no meaning, all right? What do we think we're most interested in is the pressure, the delta H, and the temperature, okay? So if I can manipulate my lines and make natural log my pressure, my x 1 over temperature, okay? Well, it says R is 8.314 joules per mole Kelvin. Why do I need joules and not liters atmosphere? Okay, well, I'm dealing with energy, aren't I? Okay, it involves energy, so I need joules. So I need to use the R with joules. Will you make some note of that? And what is the other thing I really have to be aware of? Well, look at the unit here of R. Do you see that? Joules per mole what? Kelvin. So what do you think temperature now needs to be in? Oh, I think it needs to be in Kelvin, don't you? So your X is really 1 over Kelvin, isn't it? So it says using the graphical data, it says the delta H vaporization can be determined through the slope, okay? So if you recall, your slope is negative delta H, don't forget your delta, over R. So what is H is negative slope times the 8.314, and that will be your delta H. So they're doing the math here for this particular graph, okay? So we have the slope is equal to negative heat of vaporization. So they multiplied the negative slope by R, and then they gave you the delta H, so it's 28.92 times 10 to the third joules per mole, okay? Folks, that's a positive delta H, isn't it? Go back. We're talking about vaporization going from a liquid to a gas. Doesn't it supposed to be endothermic? Hey, how do you feel when you jump out of the shower? You feel cold, don't you? Why? Because that liquid is absorbing energy from you to become a gas. It needs to be a positive number. If it's a negative number, I bet you forgot to multiply your whole term by a -1. I bet you forgot this right here. I'm telling you this from experience because I've seen it a lot through these years, all right, that people forget the negative and they give me, oh, delta H is a negative number. Well, if you think about going from a liquid to a gas, no, it is not. It has to be endothermic. Will you make a note of that it has to be an endothermic number? If not, you made a boo-boo, okay? Do that, okay? All right, so use the data below was taken to determine the heat of the vaporization of dichloromethane, okay? So here it is, here's the data, and then we plotted it. It sounds like maybe they used a Vernier probe wear, okay, and they got this, and here's the equation of the line, okay? So what is the heat of vaporization? Why don't you take a few moments out, do the math, be really, really careful, all right, of your signs, and see what you end up with, okay? Pause this and come back when you're done. Okay, hopefully you made it. And this is what I got. All right. So I took m is negative h over r. So delta h is negative slope times r. So it's negative of the negative 3773 Kelvin. How do I know that the slope is Kelvin? Your y unit is unitless, all right? You don't have a unit of natural log of p. And so it's y over x, so it's no unit over 1 over Kelvin, which gives you Kelvin, doesn't it? And then note, the Kelvins cancel out, so you get joules per mole when you do your math. So I got 31,368 because our R values in joules, this value is joules, so I convert it into kilojoules. Okay, hopefully you got the same thing. Let's see what the next page brings. So what if you don't have the Vernier software and you are not old-fashioned like I am, where I had to make all my graphs by hand, and you say, well, how are we going to solve this if the software didn't give me the slope? Well, there is a way, never fear. If the creating a graph is impractical, then use the two-point form of the Clapeyron equation. So just like in algebra, when you had y equals mx plus b to describe a linear relationship, so you can use the two-point method. y2 minus y1 equals m times x2 minus x1. So we plug this in. All right, here's my y2 minus y1, here's my slope, and here's my two temperatures. Now, wait a second, Mrs. Vanderwalle, we are subtracting here. Why are you dividing? Because we're using logs, or in this case, natural logs. What is the rule of logs? If you subtract, you're actually dividing, aren't you? Okay, so it's a natural log of P2 over P1 equals, here's our same slope, and then T2 over T1. So we can still work on this, okay? Now, it says for here, determine the heat of the vaporization in carbon tetrachloride. So I chose the first and the last one to work with. Okay, this is the two values. What happens if I use, let's say, the middle two values? Well, you'll probably get something really, really close to what I got. So it really doesn't make any difference which two numbers you pick, okay? What is important, though, is that you are consistent. So if you want 300 to be T2 and 123.8 to be P2, make sure you put those numbers. Here's my P2, that's where your 138 will go, and this is where your 300 will go. All right, so just make sure you are consistent where you put your numbers. All right, so here's my equation. And like I said, I'm going to call P2 is your 300 and 128, and I'll call P1 255 and 11.3. Okay, so again, I would label these, make a note, I would label these so they remain consistent. Don't flip-flop your numbers around, okay? So here I'm plugging in my values. Here's my P2 is your 123.8, your P1 is 11.3. Here's my heat of vaporization, which I'm looking for, and 8.314 joules over mole K is my R. 1 over 300 K minus 1 over 255 K. Okay, so now I'm going to do a little bit of math. When I did this number, I got 2.39 is equal to, I didn't do anything here. I converted these into decimals. And then in my next step, I subtracted these two, and that's where this number comes from. And then what I did multiply both sides by 8.314, and that's where this came from, okay? Notice I have a negative here, and I have a negative here. What happens to my two negatives? They cancel out, that's right. And so now I am left with the math, and I get delta H is 33,730 joules, which is 33.7 kilojoules, okay, per mole. Okay, see what the next page brings. So problem 17 says methanol has a normal boiling point. What does that word normal mean? Go back a couple pages and see what the word normal means, okay? Do that right now. All right, did you all find it? So hopefully you found that normal means 1 atm. Write that down, all right? 1 atm. So the normal boiling point at 1 atm is 64.6 degrees Celsius and has a heat of vaporization of 35.2 kilojoules per mole. What is the vapor pressure of methanol at 12 degrees? So we are looking for a p-value, aren't we? Okay, so what am I going to do here? Well, I'm going to use that same formula that we had before. Okay, there's this. Now, what can I plug in? What do I know? Oh, I know heat of vaporization. They gave that to me. There it is. I know what R is. It's a constant. Okay, well, it looks to me they only gave me 2 temperature values. Not really. They didn't. They gave you 3 because they said this is a normal boiling point, which means at 1 atm. So, do you want to make P1 or P2, 1 atm? Be consistent. Now, I want to make the denominator 1 because my math gets easier. Okay, so I chose to do it with a 1. Okay. And this got a really lengthy thing to draw out here. So natural log of P over 1 equals negative 35,200. Notice I made it into joules. Why did I make that into joules? Well, look what happens to my units. Hang on a second. My units cancel out, don't they? The joules cancel out. The moles cancels out. I have 1 over K. So my K ends up being in the numerator. Okay. Here are my 2 values. Notice I made this P1. So notice I made 64.6 T1. Okay. So then what did I do? Okay. I converted these into temperatures. And guess what I did then? I multiplied this difference by negative 3.896 Kelvin, and the Kelvins all cancel out. So now the natural log is negative 2.14. So now what do I do? Holy cow, what do I do at this point? How do I solve for pressure if I know the natural log of pressure is negative 2.14? Do you remember what you do in math class? You need to bring in the idea of E. All right, so the natural log of P equals negative 2.14. So P equals E to the negative 2.14, which is 0.118 atmosphere. And does that number make sense? Oh, but golly, I sure hope so. So if my pressure is lower than 1 atm, yes, this value is going to be lower than 64.6. So in that respect, yes. What happens if you got an answer of like higher than 1 atm? Then that would make absolutely no sense, okay? So because at a lower temperature, you're going to have a lower vapor pressure. You have fewer gas molecules being created because you have less, energy being added to the system. So that does make sense. All right, so this is problem number 18, very, very similar to the one before, okay? So what I'd like you to do is do the math all by yourself, and when you are done, come back and see how you do. So pause this, do the math, and then check your work. And I mean, you need to practice this, and I mean that, okay? So please pause and do it. Just don't watch me. Okie doke, so this is what I came up with. Hopefully you did too. So propane has a normal boiling point of negative 42 degrees Celsius. Holy cow, that's really cold. So at room temperature, it is already a gas. Here's the heat of vaporization. Notice it's kind of low, isn't it? Well, why is that? Because propane only has London dispersion forces. It doesn't take a whole lot of energy, does it, to break it up? So what's the vapor pressure? Basically at room temperature. Well, you have a lot of gas molecules, don't you? So let's check out what we have. So here I made ATM the small, or the denominator, excuse me. Why? Because it makes your math a little bit easier, okay? And here's my negative heat of vaporization. Here's my R. Notice I used my T2 is the one I'm trying to find, all right, because I'm looking for P2. So here's my T2 at room temperature. And this is the negative 42 degrees Celsius. That's at 1 atm. That's the normal boiling point. So then what did I do? I took these two numbers and divided, and I got negative 2290. And then I did 1 over 298 minus 1 over 231, and I got a negative 0.0009733. So then I multiplied those two numbers together. Notice the negatives cancel out to be a positive. And then I found how do I get rid of the natural log? I made it to an e value. And then e to the 2.23 is 2.72 ATM. Does that number make sense? I don't know, does it? I hope so, because we know from its normal boiling point, it's 1 ATM at negative 42. So what happened? We increased the temperature by a lot, didn't we? And so I would expect to have more pressure. It's not because I have more molecules, it's because they're all going very fast, and so they're going to have more collisions, so I'm going to have more vapor pressure. So I really hope that all makes sense. Well, I see we're done with this problem, so as always, don't wait to be great, and we did finish section 11.5. See you later. Bye-bye.